Hey everybody, welcome back. Long time no see. Hope you guys had a little bit of a break to work on the homework assignment. So we're gonna just get right back to it. So in this unit, we're gonna talk about Markov chain Monte Carlo in a lot more detail. And in this unit specifically, this part one, we will cover Metropolis-Hastings and Gibbs sampling. And I'll be focusing on a conceptual introduction. So in some classes, you will see, an exercise like recreate a sampler. But for this class, I will be emphasizing a conceptual understanding of MCMC so that kind of demystifies what is going on, so to speak. Just a really brief review of why we're going to the MCMC world. So we came from the grid approximation world, where you compute the posterior for every single combination of, say, 3-4 parameters. So it's very computationally wasteful because you are computing the posterior where the probability of that particular parameter combination is almost zero, yet you're still computing the posterior. Almost all realistic analyses are far more complex than that. So almost every regression model has more than 3 parameters. And so we need to have a way of sampling from the posterior without computing it at 1 million data points. And the big idea is we want to sample from more dense areas of the posterior. More. We want to sample from the more dense areas of the posterior where that particular combination of the parameters is more likely. First things first, let's unpack the definition Markov chain Monte Carlo. So this is Mr. Markov, Andrei Andreevich Markov. Looks like that's circa 1886. He's got a beard and a half. So a Markovian process is a process that only depends on the previous state or position. A Markov chain is a sequence of positions. And actually going forward, thinking of the MCMC as picking off a set of coordinates in space, it will serve us very well. And these are coordinates on a line when we have 1 parameter, coordinates on a plane when we have 2 parameters, coordinates in a cube when we have 3 parameters, so on and so forth. Monte Carlo is just a computer simulation. So when we put everything together, we get a computer simulated sequence of positions that only depends on the previous state or position. So to start, I thought I would actually go ahead and just use the book. McElreath goes through a very helpful heuristic where we have a kingdom, an archipelago of 10 islands. Island 1 is the smallest island. Island 10 is the biggest island. And there are islands 2 through 9 that are varying sizes. The big idea is that the king wants to visit every island number of times that is proportional to how big the island is. So to be clear, what this means is we want to visit island 10 times more frequently than island 1 in the long run. And we want to visit island 10 twice as often as island 5 in the long run. And 5 times more frequently than 1 in the long run. So this is a heuristic, but we're building a posterior distribution without having to compute something at all 10 islands. So this is something that I will, we're going to build this, and this will appear again and again as we're learning Markov chain Monte Carlo. So we will arbitrarily start at a position. So I picked the biggest island. You can pick any all that. So this starting point is arbitrary. So the first random event is we essentially flip a coin to decide which island to consider, but we're not going to make a move yet. So it's We flip a coin and just randomly decide if we're going to go to island 1 or island 9. Next, so at random, we pick 9. We're going to compare using a ratio. We're going to compare the size of the proposed location to the size of your current location. All right, so we do proposed over current. And in this case, it's 9 over 10, which of course makes a ratio of 0.9. So this ratio is called the acceptance ratio. And as the name indicates, it will have something to do with how often you will choose to move to this island, to that spot, to that position. All right, now we're at number 4. Compare this ratio. Compare the ratio to a random number between 0 and 1. So remember, this ratio was 0.9, and we're now going to be generating a random number between 0 and 1, and then comparing our ratio of 0.9 to a number between 0 and 1. You might kind of guess what's happening, which is if our acceptance ratio is greater than a random number from the interval 0 to 1, we make the move. So the random number that was generated between 0 and 1 was 0.32. My acceptance ratio was 0.9. But now that you kind of know how this works, and again, you start at an arbitrary location, you flip a coin to see which, where your proposed island is going to be. You pick your proposal at random. So we started at island 10 at random, and we at random picked 9 as our proposal. You go proposed over current. This gives us a number called the acceptance ratio. You then compare the acceptance ratio to a number between 0 and 1. Our acceptance ratio was 0.9. So we were very likely to move, regardless of what step 4 produced. So yes, there was a chance. There was only about a 10% chance that we were not going to move, and a 90% chance that we were going to move. So us moving from 10 to 9 is actually quite a likely result. Okay, now we're at 9. Now I'm at 9. I will randomly pick which island I will consider. And I, at random, have selected 8. Proposed over current, here is my acceptance ratio. All right, acceptance ratio, 8 over 9 is 0.889. So we're going to be comparing this to a number, a random number between 0 and 1. And you might imagine that we are very likely to move again. Because the chances of us being greater than any number between 0 and 1 is about 89%. So we are about 89% likely to move from 9 to 8. I'm going to generate a random number between 0 and 1. That random number was 0.93. Well, because 0.93 is not greater than my acceptance ratio, I'm going to stay. So formally what this means is I have rejected the proposal. I have made island 8 my proposal. I computed my acceptance ratio. I came up with a random number between 0 and 1. And based on this comparison, I have rejected the proposal. And so we just simply stay at 9. Okay? We're still at 9. We pick a random number, a random island to consider next between 10 or 8. So this is the trying to simulate the Markovian property, where we can't just jump from 9 to 4. Our positions, our future positions are dependent on our previous positions. So we are coming up with a heuristic that tries to, as closely as is reasonable, resemble what a real MCMC looks like. So after this example is done, I will show you what a MCMC looks like in 2 dimensions. But for now, let's just roll with it. Let's get all the steps right. We're still at 9 because we rejected the move to 8. By the way, if we again selected 8, if I, at random, I very much could just go ahead and select 8 again. And then my acceptance ratio of 0.89 will be compared to a random number between 0 and 1. And I remain very likely to move from 9 to 8. So I can come up with the same acceptance ratio, but the result will be different because step 4 is a random event. However, this time, I at random pick 10 as my proposal. Okay, my acceptance ratio is proposed over current, which is 10 over 9, which is a number that is greater than 1. So if you're following along at home, we'll be comparing a number that is greater than 1 to a random number between 0 and 1 inclusive. And if our acceptance ratio is bigger, we will make the move. We are 100% likely to move. So what this algorithm ensures is that we will always step up in the posterior. We always step up. In the posterior. And we should always want to step up because we want to home in on that most likely area in the posterior. So if we are starting out in a tail and at random we found where the peak is, we want to go to the peak like all the time. It's the reverse that we don't want to do as often. If we're at the peak, yes, we want to go back to the tail, but we don't want to go back to the tail nearly as often as we go to from the tail to the peak. I think I said that right. With an acceptance ratio of 1.11, we are guaranteed to make the move. I'm still going to generate a random number between 0 and 1, which happened to be 0.047. So we were likely to beat this number with just about any acceptance ratio, but this one we are guaranteed to make the move. And so I am now back at island 10, and my posterior gets updated with my new position. So if we speed this up, here is 100 such steps. So I did 3 such steps. Here is 100 steps. Here is 1,000 steps. And here is 10,000 steps. So remember in activity 1, when we're taking random samples from a beta, we start to approach the true distribution the more samples we take. And so if you look at what's happening, you know, island 10 is known to be 10 times bigger than island 1. After 100, we're not quite getting it. Island 10 doesn't show up nearly as much as island number 8. Island number 8 is the most likely position, and island 10 is actually less likely than a whole lot of them. So this is not the true posterior distribution. After 1,000 samples, we start to get close. Island 10, the biggest island, known to be the biggest island, is now the most likely result. But is it quite 10 times bigger than 1? Is 10 twice as large as 5? Is 5 5 times as large as 1? So to get the posterior exactly right, they have to let it go for a lot longer than 1,000 samples. So at 10,000 samples, we start to get to where we need to be. So this is now converging to the true posterior. So in a little bit more formally, by the way, the difference between a a metropolis and a Metropolis-Hastings MCMC, by definition, is that the metropolis can only use symmetric proposals. So the distribution that decides where your proposal is, that you then plug into the acceptance ratio and you compare it to a random number. That distribution that decides where your proposal is in a Metropolis MCMC is only limited to be symmetric. But that's why it's not used very often. So the Metropolis-Hastings allows that proposal distribution to be asymmetric. And that's important because for things like sigma squared, we don't want something like a normal 0, 5 on our sigma or sigma squared, right? Because the standard deviation and variance can be negative. So for a lot of parameters, we need these asymmetric proposals to have any sort of logical sense. So the Metropolis is really not used anymore. The Metropolis-Hastings is used, and it goes with the same sort of idea. We pick an arbitrary location, we make a random proposal using an asymmetric distribution, possibly asymmetric distribution. We compute the acceptance ratio by taking the posterior at the proposed location over the current posterior, and we compare that to a random number between 0 and 1. If our proposed over current is greater than the number, we make the move. If not, we don't make the move. And then we start again. And we do that 10,000, 100,000, a million times. The more times we do it, the closer we're getting to the true posterior. So here's the other little bit here. We haven't seen this marginal distribution in a little bit of time, but I wanted to make a small comment here. So you should recognize these two quantities as the full posterior at the current location, right? Here is the likelihood evaluated at the current set of parameters. Here is the prior of the first parameter and the prior of the kth parameter. And then here is our proposed location. So this is the one we generate at random from our proposal distribution. Here is the likelihood at the new set of parameters. And then here are all the priors evaluated at the new set of parameters. This one could be the prior for the mean, the prior for the sigma. And then we have to perform that integration, right? Remember that the marginal distribution, it integrates the joint distribution. And that's why we don't like it. It's because this is usually a pretty nasty integral to compute. First of all, this joint distribution can be tough, and the integration is a tough computational exercise to compute. But if you think about the acceptance ratio, if we're thinking about the acceptance ratio, our proposed over the current, and you can see where I'm going with this, is that it's actually the same y, right? Y is independent, it's the same y. It's the same P of y. It's the same marginal distribution because I didn't spell that right. It's the same marginal distribution because it's independent of the current position of the parameters. This function doesn't depend on theta, and so it's exactly the same thing. So we're just going to cancel it out. And then the acceptance ratio becomes just a function of the likelihood evaluated at the new set of parameters and all the priors evaluated at the new set of parameters over the likelihood evaluated at the old set of parameters and all the priors evaluated at the old set of parameters. We no longer need this marginal distribution to make the MCMC run. And that's just a thing of beauty, because otherwise MCMC would take a very, very long time. So let's roll through a little little bit more realistic case of a two-dimensional, two-parameter Metropolis-Hastings. So I'm about to flip into my browser, and the blue density is our true posterior. In reality, you would never observe this, but this is just, we're just learning here. It's the true posterior. And this is aptly named the banana distribution. There is actually a formula for the banana distribution. We will be starting at a random location. We'll be using a two-dimensional multivariate normal to generate a proposal. So by the way, a two-dimensional multivariate normal produces a vector, right? A vector with two elements. And that's how we're going to know to go from this spot to this spot. How aggressive this proposal is will depend on the proposal standard deviation, right? A one-dimensional normal distribution has a standard deviation, and a 2D multivariate normal has a standard deviation. Because of the circular contours, you know those standard deviations are identical. So this has a standard deviation of 1. That is something that you would tune. So the proposal standard deviation is something that you will need to tune to your specific data set and model. And that is something that we're all going to struggle with in the next activity, is tuning our Metropolis-Hastings distributions, samplers. And how can I make this close? I did it. All right, let's take a look. This link will take you to a GitHub page that I already have pulled up right here. If you don't, if you're just coming in, this checkbox will be on, and so it will just start sampling right away. I turned it off because we want to do it together, and we want to make predictions to make sure we understand how the MCMC works. You can, by the way, change the target distribution, and I will in a sec. You change various visualization exercises, and you can also tune the proposal. But let me just start with 1, which is the default. Again, the blue is the true posterior that we're trying to find by randomly searching and performing that heuristic that we just saw. Here is our random starting location. So if once we triangulate that random starting location, will be somewhere right over there where my cursor is. So let's do it. Boom. There is my current location at random, and I have just generated a proposed location from a two-dimensional multivariate normal, from right over here to right over here. Looking at this, right, we're thinking back to the acceptance ratio, likelihood times all the priors at the current location, at the proposed location over likelihood times all the priors at the current location. You know, it looks like we're staying at about the same height, right? We're staying at about the same height. If we're staying at about the same height, that ratio is probably going to be close to 1. If that ratio is close to 1, we're comparing that acceptance ratio to a number between 0 and 1. So this means we're very, very likely to make this move. We're almost certain, in fact, and I'm setting myself up to fail, but this is live. We are near certain to accept this move. Let's do it. And failed. And this is a reminder that although that acceptance ratio is very close to 1, we're still comparing it to a random number between 0 and 1, and it chose not to make this move at random. So we stay right back at our initial location, and we will now generate a new proposal. All right, well, this one, I'll tell you what, guys, if I get this wrong, y'all can quit the class, because right here, our current is somewhere on the posterior, and we're just moving into the nether space. So our proposed is almost 0. The height of the posterior at our proposed location is almost 0. The height of the posterior at our current location is not 0. So proposed over current is 0. Comparing this to a number between 0 and 1, we're not going to accept this proposal. Yeah, we're not going to accept this proposal. Good, good. Stay in the class. All right, you got this one, right? Remember, we always step up. My current is some number, but my proposed is a number greater than it. So your acceptance ratio is proposed over current. That number is now greater than 1. We are guaranteed to make this move. There we are. Now, we're going to start making our next proposal from that new location. Let's do it. All right, very interesting. Tough choices, but we are staying about equal level, right? If I'm counting, and then here is the first kind of dark contour, second, third, and here is the first, second, third. This is a little bit of a step down, but I think we're still quite likely to make this move because that ratio is going to be near 1, and we're not. This is staying on equal. In fact, it's within that little contour. So our acceptance ratio is near 1 here. We're going to make this move. This is going from a height posterior of something to a height posterior of 0. 0 over anything is 0. We're not going to make this move. This is a step down. So when we're stepping down, you can think of it as a number between 0 and 1 compared to a number between 0 and 1. I have no idea. I'm not going to make this. I've already gotten 2 wrong. I'm not going to make this call. Looks like we took this step, and that's a good thing, right? We want to explore the tails. If our sampler never took a step down, then we would never, ever get to the tails. This is a step up. A step up we always make, right? Now the proposed posterior is greater than the current posterior. Our acceptance ratio is greater than 1. We are guaranteed to make this move. All right, this is now a step down. So you call it something between 0 and 1 compared to a number between 0 and 1. That time we decided not to make a step down. Here it looks like another step down, but that time we decided to do it. Let's do a couple more. Not going to do it. This is a step up. We're going to do it. Step down, maybe. Not going to do it. Maybe 50-50. Not going to do it. Staying equal, likely. Not going to do it. Not going to do it. Still not going to do it. Staying about at the same height. That time didn't do it. This is a step up. This is not going to happen. All right. So this is good practice to at least understand the cases where we're stepping off into nothingness, like it's going to happen right now, and the cases where we're stepping up like this one, where it is absolutely going to happen. And then the tough cases that, well, it's random, are the cases where we're staying on about equal plane, and that's the ones that I got wrong. I have no idea because that acceptance ratio is some number between 0 and 1, and we're comparing it to a random number between 0 and 1. So I hope I got about half of them right. Okay, so if I just kind of let this run, you guys can see that if I reduce the delay, it will go ahead and without knowing what the distribution function of the posterior is, we are starting to get a look based on our samples alone at the banana distribution. If I let this run enough, eventually, by looking at our samples, which are the dots on the screen, we will absolutely reproduce the banana distribution. But look, right now, it's stuck on the right-hand side, and it's refusing quite yet to make its way to the left-hand side. So the left-hand tail down here is unexplored. If you didn't know there was anything there, if you right now cover up the left-hand tail, you're never going to know based on the samples that it exists. Not going to know. And you can see how many red arrows are popping up. Your computer has to use electricity. Your computer has to perform a computation every time an arrow pops up. The only things that make it in your sample are the dots, are the green arrows. The red arrows don't make it into your sample. And by the way, as we were talking, I can tell you that as the number of samples approaches infinity, it will eventually explore this entire distribution. Okay. So let's play around with something here. What is your guys' intuition if I now reduce the proposal standard deviation fivefold? Well, I'm going to start in the nether space, and I will go into the nether space. I'm not going to take this one. Given that this is 2 standard deviations, right? So I am 5% likely to produce a vector outside of this second circle. How long is it going to take me to get to the banana distribution? How long is it going to take me? Probably forever. This is a step up. Officially, it's a step up because I'm getting closer to the posterior. It's another step up and a step down. And might be going towards this tail, so who knows. Step up gonna happen. Step up gonna happen. Marco Polo, I'm just gonna let it go. And we'll see how this guy moves. All right, now we're finally found, right? We migrated to the posterior. And some of the pictures I showed you, right? Those chains can start off the posterior and migrate to the posterior. So I hope this little simulation shows you how that happens. You just continually try proposed over current. That's your ratio compared to a number between 0 and 1. Move if you're greater. All right. So we are accepting more samples. There's a lot more green arrows than in the other example because we're not going too far out on the limb, right? We're less likely to step off the posterior because our proposal standard deviation is just so small. But we're also less likely, as I'm about to say, get into the tail. We're less likely to get into the tail. Now it's going to be sampling that left-hand tail until it's blue in the face. And how likely is it to migrate to the right-hand tail? Now, we are recording live, and I have not, this is a random event that we're watching here. But if you, at this point, if you cover up the right-hand side of your screen, you would never know that right-hand tail existed, right? So right now, you're not representing the banana distribution very well. You guys can play around with this. The other approach, don't autoplay, reset, is let's juice up the proposal standard deviation to now be 2. We started with 1, I took it down to 0.2, now it's 2. So I'm gonna start at the crosshairs right around here. All right, I'm gonna step, all right. Now what? Now what? So it looks like we're going from a tail location and we're stepping just off the distribution. So this is actually a 50-50-ish shot. It didn't happen for us. All right, we're gonna step off. Whoop, not gonna happen, not gonna happen. That was a step up. 50-50, not gonna happen, not gonna happen. It's equal height, yeah. So that's a step up, that was a guaranteed one. Step down, so call it some number between 0 and 1 compared to some number between 0 and 1. So if I let this go, you should be seeing a heck of a lot of red arrows. So we're doing a lot of computation and we're gonna be jumping around the different positions. But this is a lot of wasted computation. We're having trouble tuning in where that posterior distribution lies, right? This sampler doesn't see the blue banana. It just does proposed over current compared to a number between 0 and 1. Actually, I kind of like how this is going a little bit more, right? Remember, when effective sample size is even in a few hundreds, we can still make pretty decent inference. So I think this is going better than the case where our proposal standard deviation was 0.2. All right, enough of this for just now. Those are the notes that go through several iterations that we just went through. And feel free to play around with different kinds of distributions. Several options are out there. So the strengths is that this random walk, random touch, for the lack of a better word, is relatively easy to understand. You are simply randomly generating a location, and you are comparing the posterior at your proposal to where you are now. It's very general. You can use any combination of priors and likelihoods. And if you can write your log posterior being proportional to the log likelihood and all of the sum of your log priors, you guys should have seen this before. All right, you guys saw this in activity 2. If you can write your model as the log posterior proportional to log likelihood plus log prior, log prior, you can run the Metropolis-Hastings MCMC. And there is relatively little computational burden per iteration. It's just as long as it takes to compute your posterior 2 times, right? 2 times ratio, make the decision. 2 times ratio, make the decision. So you can take a lot of samples very, very quickly. And as a reminder, no need to integrate. So, you know, you can just go ahead and put in 1 million samples and go get yourself a drink. When you come back, maybe you would have converged to the posterior. You're only guaranteed to converge as the number of samples approaches infinity. But we live in finite times, and we need samplers that are a little bit more efficient than that. How random your random touch, random walk is, needs to be tuned. If your proposal standard deviation is too low, you will be stuck making proposals that are too, not aggressive enough, too conservative. If your proposal standard deviation is large, you're too likely to step off the posterior into nether space. So you need to be somewhere just right. And what just right means is model and data set specific. The other big issue, our little visualization did not account for the fact that subsequent steps, even when accepted, the subsequent steps are autocorrelated. And so if you take 100,000 samples, you're not going to get 100,000 effective samples. The effective sample size is almost always less than the number of samples. And what makes it frustrating, I have not seen a ton of articles that explicitly list their effective sample size. If your effective sample size is too low, then you could be claiming certain findings based on a posterior distribution that is not well approximated. It's only when you have effective sample size that is large, and what small and large means is hard to come up with a rule of thumb. Usually in the literature, people let their samplers run until the effective sample size is close to 1,000. But if your samples are super autocorrelated, you might need to make 100,000 samples to get effective sample size of 1,000 out of that. Here is that same issue in a little bit of a better sort of comparison type figure. So this figure is actually out of a textbook by Krushke. And it just takes our Bernoulli globe toss example from activity 1, the random coordinate example. If you look at the observed proportion of being 14 out of 20, and now you're generating samples of probability of water from the posterior. So here we're comparing 3 different proposal standard deviations. Too small, too large, and yes, the middle is just right. So when you're, and you guys saw this in 2 dimensions, but sometimes it's helpful to kind of bring it back to 1 dimension. All right, we took 50,000 samples. We only got an effective sample size of less than 500 here. We took 50,000 samples. We got an effective sample size of, call it 12,000 here and 2,000 here. When you're taking when your proposal standard deviation is too small, you're way too stuck, right? That chain doesn't move as much. It takes forever to get to the tails. You start in the one tail, and only towards the end do you get into the right-hand tail, right? You're starting in this left-hand tail. Only towards sample number 50,000 do you get into the right-hand tail. And it looks like your average acceptance rate is 94%. So you accepting a lot of samples, you're accepting a lot of new positions when you really shouldn't be. Let's go the other side of this coin. Well, if your proposal standard deviation is too large, then you're stepping off the posterior. You are stuck at a single position for a long time because your sampler doesn't accept a new proposal. And so, your entire sampling scheme is kind of like this sets of just a few positions. Your acceptance rate is only 6% here, and your positions are so autocorrelated. Only 2,000 effective samples out of 50,000 requested samples. So I hear you asking the question, how do I know what just right is? It's model and data set specific. You tune it. You would come up with your regression model, come up with a reasonable set of priors, and then a reasonable set of proposal standard deviations, and then let it run for like 5,000 iterations. It's going to be pretty quick, hopefully. If you're not inverting too many matrices, it's going to be pretty quick. And then you would plot your trace plots, right? This is just a trace plot, by the way. You would plot a trace plot. You would compute your effective sample size, compare to how many samples you requested, and then make a call. Man, like my samples are way too autocorrelated and my chains look like they're meandering very slowly, or my chains look like they're stuck. And so whether it's meandering very slowly or stuck at only a couple of positions is how you know whether to go down or up in your proposal standard deviation. There are rules of thumb about what acceptance proportion to look for. Anytime a rule of thumb exists, question it until the end. Yeah, 30 to 50% is probably okay. If you're seeing 6% or 90%, you're nowhere close. But there could be a lot of evil done within 30 to 50%, to be clear. That's why you always plot your trace plots, you always compute your effective sample sizes, and you always run multiple chains to make sure no matter where you start your chain, you converge to the same posterior. Here is a figure from our author illustrating the same concept, which is if your proposal standard deviation is low, you're not going to get to the other tail if you just so happen to start in this tail. If your proposal standard deviation is too high, and by the way, here, you go from 0.1 to 0.25, it's unclear to me that that would automatically be high. But now, you're only taking a small proportion of samples into your posterior. You're doing a lot of wasted computation with these open circles. So the filled in circles are the samples that are accepted, and the open circles are the samples that are rejected. Only the closed circles are the ones that make it into your posterior where you make computation for both. And remember, we need several thousands, 10,000 plus, roughly speaking, to make sure that we are, we can even claim that we have converged to our true posterior distribution. So this speaks to the inefficiency. This is inefficient, right? Metropolis-Hastings is fast. It is fast comparatively, but inefficient. Unless you just nail that proposal standard deviation, like is just right from the get-go, which almost never happens. Inefficient. Okay. We're almost done for today. Where we're headed next is, well, Metropolis-Hastings still is being used, and it's a good starting point for us to understand the several random decision points inside of an MCMC sampler. The next one is Gibbs, and it is a completely different animal because there are no formal random proposals and nothing ever gets rejected because we're going to be following preset recipes. There are a number of known combinations of priors and likelihoods that produce known combinations of posteriors. So they have names and they have formulas for their parameters. So the example that we're going to look at when we come back next time is if our likelihood is binomial and our prior is a beta, then our posterior is a beta with these parameters. So if we have a problem where the data likelihood is binomial and we're really good at setting prior using the beta distribution, beta is very flexible, so this works in many cases, just for one parameter, of course, then your posterior is known to be a beta distribution. If your posterior is known to be a beta, you don't have to do this random search. You don't have to do this random touch and feel. You can just go ahead and generate observations from your beta. And you can see what's inside of your posterior is a combination of hyperparameters and beta. So that's a quick preview for what we're going to start with next time. Play around with this little tool. Drop a comment on our discussion board. And thanks for your guys' attention. I will see you next time. Do your homework. Bye-bye.